Hello everyone, welcome to this lecture. Today we will be talking about copying objects. It seems really simple at first because most of us has copied objects thousands of times already. When we write integer b equals a and assign a to b, we don't really have to think about it that much. With objects, things become a little bit more interesting, you could say. Sometimes copying an object is exactly what you want, it copies directly, but sometimes it quietly creates bugs that are extremely difficult to track down. In fact, some of the worst memory problems in C++ are because an object was copied in a wrong way. So that's what we will be going through in this lecture so that it doesn't happen with us. But before we get there, let's quickly refresh two ideas that we will rely on this lecture. So let's quickly remind ourselves how memory works in C++. You have already seen that memory is generally split into two important areas, the stack and the heap. The stack is the easy one. Local variables live there and C++ manages them automatically. If I write int x equals 5, that memory appears when the variable is created and disappears automatically when the function ends. The heap is different. We ask for memory ourselves using the keyword new. For example, you could see that this is how we ask for a new chunk of memory. And this one creates an array of 5 integers somewhere on the heap. Now, here's the catch actually. That memory does not disappear by itself in C++. It assumes that because you asked for it, you are also responsible for cleaning it up. If you forget to call delete or something like delete, the memory stays allocated, and that's what we call a memory leak. Keep that in mind because it's the main reason copying objects become really tricky. Now let's connect that idea to class objects. Every object has a life cycle. It has a beginning and it has an end. When an object is created, its constructor runs automatically. If the object owns heap memory, the constructor is usually where that memory gets allocated with the new keyword. Later, when the object goes out of scope, its destructor runs automatically. The destructor's job is very simple. Clean up whatever resources the object owns. That often means calling delete keyword to free heap memory. So you can think of constructors and destructors as a team. The constructor acquires resources and the destructors release them. As long as every object owns its own resources, everything works nicely. The interesting question is what happens when we copy one object into another one. That's exactly why today's topic is quite important. At first, copying an object sounds obvious. You make another object with the same contents and you are done. That should be it, right? But C++ actually copies objects much more often than many people realize. One common example is passing an object by value to a function. The compiler creates a copy, Then it passes that exact copy to the function where it starts executing. Another example is returning an object by value from a function. Again, copying may be involved. The important point is that these copies are often created automatically by the compiler. You don't always write code that says copy this object. That's why understanding copy behavior isn't optional in C++. Even if you never explicitly copy an object yourself, the compiler may still do it on your behalf. So, before we study how C++ performs copying, let's agree on what a successful copy actually means. All right? When we copy an object, the new object should represent the same state as the original. How that happens depends entirely on the class. For a small mathematical object, like a complex number, copying may be nothing more than copying a couple of numbers. For a string class, things are more complicated. The object may need to allocate new memory and duplicate the characters stored there. This is why there isn't one copying strategy that works for every class. The compiler can make a reasonable guess, but it can't always know what your intention is and what you will do with your classes and your objects. That responsibility often belongs to the class designer. That makes sense. So, this leads us to the default behavior in C++. If you don't write any copy logic yourself, the compiler generates a hidden copy constructor for your class. That generated copy constructor performs what's called a member by member copy, also known as shallow copy. Here, each member variable is copied into the new object. For many simple classes, that's perfectly fine, but there's one important situation where it breaks down. If your class owns dynamic memory, simply copying the member variables is no longer enough. So instead of just talking about it, let's see what the compiler is actually doing. So here, let's create our first file of the day, which is example1.cpp. Let's include IOStream. Then use the namespace of standard. Then let's create a small class. Sorry about that. Class point. And here we will have two variables, x and y. Then we will store it like this. Here's the semicolon. Now, notice that I didn't write any kind of copy constructor at all. So, integer main, let's see, we will create 2 points. Point P1 will be 3, 5, and point P2 will be P1. So now we will do something interesting. We will access the P2X and we will put 10 there. Now we will see out and see what's going on in there. So at first, we will print p1x, then comma, then p1y, and then end line. Similarly, we will see out p2x, and then put a comma, and then p2y, end line. Now let's run this. As you can see that I changed P2, but it didn't affect P1 at all. Each integer member was copied independently, and this is exactly the behavior we expect from a simple data member. Now let's see what happens to one of those members if they are a pointer. So before that, let's get back to the slide. So here, as you can see, we are talking about dynamic memory now. So everything looked fine a moment ago because our class only contained integers. Now let's replace those integers with dynamic memory. The compiler still performs the same member by member copy. The problem is that copying a pointer copies only its address. After the copy, both objects believe they own the same block of heap memory. So at first, nothing seems wrong. The trouble appears later when one object changes the data or when both destructors try to free the same memory. So let's go ahead and build something small. Let's create a new example, not here, it should be under lecture 8, example 2.cpp. Now, of course, we will need to include IO stream. Then we will use the namespace standard. Then let's declare a class of number. Here we will have our pointer. So let's go ahead. Here's the integer pointer value. And when the constructor is called, integer value should be our new integer value. And then we will also create a destructor, which is number, and it will delete the value. We are allocating memory here and we are deleting the memory here. Let's create our first number. The number, we will copy it like this, and then we will access n2 value, and then we will put 20 there, let's say. Now let's check what's going on. Okay, so we will see out n1 value and then see out n2 value, and then we will return. Let's run it. So there should have been 5 and 20, right? But we are seeing that once we accessed n2 value and put 20 there, it also changed n1. This is the problem we will spend the rest of the lecture learning how to solve, because In simple programs like this, it might not create a huge mess, but when you create complicated objects, like let's say a character from a game with multiple features and multiple activities that they will be doing inside the game, it might create some unreasonable problems that are totally reasonable in the eyes of C++, but not to the programmer. Okay, let's get back to our slide. We just saw that copying isn't always simple as it looks. So it's useful to separate copying into three different ideas. The first one is reference copying. Here, we don't create a new object at all. We simply create another name for the same object. The second one is shallow copying. A new object is created, but its member variables are copied exactly as they are supposed to be. If one of those members is a pointer, only the pointer value is copied. The third is deep copying. This is usually what we want for classes that own resources. Not only the object is copied, but all the resources that belong to that exact object are duplicated as well. We will look at these one by one because they solve very different problems and we need to know which problems they are going to solve. So let's start with the simplest one, reference copy. It's actually a slightly misleading name because no copying happens. A reference in C++ is simply another name for an existing object. If you look at the diagram, notice that there is only one object in memory. Both names point to exactly the same thing. So creating a reference is almost free, no memory allocation happens, no constructor runs, no data is duplicated. That's why references are used so heavily in C++. They're fast and they avoid unnecessary copying. The trade-off is that there is still only one object and every reference sees exactly the same state. So here's what that looks like in code. If I write this, here the ref keyword is not a second integer. It's simply another name for original. So if I change ref, original changes immediately because they are the same variable. The same idea applies to objects. When we pass an object by value, the entire object is copied. That can be expensive for large objects. When we pass by reference, no copy is made. Most of the time, the best choice is a const reference. It gives us the efficiency of passing by reference while also preventing accidental modification of the original object. You will see the const class name and everywhere in modern C++ because of this exact reason. Now, let's compare this with languages like Java. In Java, variables that store objects are really references by default. Two variables can easily refer to the same object. Changing the object to one variable immediately affects the other one. In C++, that's not the default behavior. Objects are real objects, not references. You only get reference semantics when you explicitly use the AND operator. You can see in the diagram earlier that both references lead to the same object. There's only one copy of the data. That's why reference copying is extremely fast. But it's also why it's only appropriate when both names are intentionally sharing the same object. If one piece of code expects an independent copy, references are the wrong tool. Now let's move to shallow copying. Here, unlike references, shallow copying does create a second object. If you look at the diagram, you will see two separate objects. Each one has its own member variables. So far, that sounds perfect, but the problem is hidden inside the pointer member. Both objects contain exactly the same pointer value. That means they both point to the same heap memory. So we have created the object itself, but we haven't created the copied resource that the object owns. This is exactly what the compiler generated copy constructor does that we have seen earlier. This explains the strange behavior we saw a few minutes ago. Because both objects share the same heap memory, changing that memory through one object immediately affects the other. The objects look independent on the outside, but internally they're still sharing data. The diagram illustrates this nicely because you can see two objects at the top, but both arrows lead to the same heap allocation underneath. Languages like Java often use similar shallow copying mechanisms for cloning objects. In C++, shallow copying is often acceptable for classes that don't own resources. For classes managing heap memory, it's usually a bug waiting to happen. Now, deep copying solves that problem. Again, we create a second object. The difference is that we also create a second copy of every resource that belongs to the object. Just look at the diagram. This time, each object points to its own heap allocation. The data may contain the exactly same values, but the memory is completely separate. Now, changing one object won't affect the other one. Each object owns its own resources. This is generally the safest and most predictable behavior for resource managing classes. So, deep copying sounds like the perfect solution. So, why doesn't C++ always do it automatically, right? The reason is that the compiler can't always know what should actually be copied. Imagine a book object. The book might store its title and author. Those clearly belong to the object state, but it might also contain a pointer to the library that owns it. If we copy the book, should we also copy the entire library? Probably not. The compiler can't answer questions like that. Only the programmer, who's the designer of everything, knows which resources truly belong to the object and which pointer simply refers to something else. That's why C++ lets the class designer define exactly how copying should work. The tool we use for that is the copy constructor. A copy constructor creates a new object from an existing object of the same class. Its parameter is almost always written like this. Notice the parameter is a reference, and that's essential. If we passed the object by value instead, the compiler would need to copy the object just to call the copy constructor. We don't want that. That copy would call the copy constructor again, and then again, and then again, so it would never end. Using a reference avoid the infinite recursion. If we don't write a copy constructor ourselves, the compiler generates one automatically, as we have already seen. But what we saw was that generated version was a shallow copy. For classes that manage dynamic memory, we will usually replace it with our own implementation that performs a deep copy. So far, we've only looked at copying a single class. But what happens when you inherit something from another class? Inheritance adds another layer. A derived object actually contains two parts. It contains the base class part, and then it contains its own additional members. You can think of the derived object as being built in layers. The base class forms the foundation, and the derived class sits on top of it. When we copy a derived object, both layers have to be copied correctly. The base class already knows how to copy its own data, so the derived class shouldn't try to do that work itself. Instead, its job is to call the base class copy constructor and then copy its own members. So let's see what that looks like. Here we will create example 3. So let's say we have a class person. Okay. Here we are gonna have our constructor, and the constructor will look like this, which will say other, and let's say we will do something there. And then let's say we have another class named student, which will actually have another constructor. So the important line is this one. This forwards the copying of the base part to the base class. Then the derived constructor can copy its own members. Now let's see what happens if we forget that step. Suppose we write the derived copy constructor, but never call the base class copy constructor. The compiler still has to construct the base class somehow, right? The base part is no longer copied from the original object. Instead, the compiler calls the base class's default constructor. That means the base portion starts with default values instead of copied values. The derived part may be copied correctly, but the base part is not. That usually produces an object whose state is only partially copied. Let's see an example. So here, when we remove this, let's say, this compiles if person has a default constructor, but it doesn't produce a proper copy. Whenever you write a custom copy constructor for a derived class, remember to initialize the base class in the initializer list. Let's come back to the compiler-generated copy constructor. If we don't write one ourselves, C++ automatically creates one. That's convenient because it saves us work for simple classes. But remember what it actually does. It performs a shallow copy. For classes containing only ordinary values, that's perfectly fine. But for classes managing heap memory, file handles, sockets, or other resources, it's usually not enough. Two objects end up believing they own the same exact resources. Eventually, both try to release it. That's how double deletes and memory corruption and undefined behavior appear. A good rule of thumb is if your class owns a resource, don't rely on the compiler's default copy constructor. Write one that expresses exactly how ownership should be copied. Sometimes the right answer isn't to copy an object at all. Think about a database connection or a file stream or network socket. What would it even mean to make an exact duplicate? Often copying simply doesn't make any sense. Older C++ code solved this by making the copy constructor private. That stopped code outside of the class from copying the object. But look at the last question on the slide. Is the issue resolved now? Not really. It's more of a workaround than a clean solution. There are still situations where the class itself or its friends could accidentally perform the copy. Modern C++ gives us a much better approach. Starting with C++11, we can state our intentions directly. If we want the compiler-generated copy constructor, we simply write equal default. That tells both the compiler and anyone reading the code that the default behavior is exactly what we want. If copying should never happen, we write equal delete. Now, any attempt to copy the object becomes a compile time error. It's explicit, it's easy to read, and much safer than hiding constructors in the private section. So let's see an example of that. It's example 4 now. Let's say we have a database class and we have our constructor here. We will say that we want the database to behave like default. So the default behavior is expected. Now, integer main, what we're going to do is we create a db1, database db1, db2 equals db1. You can see that cannot be referenced. It is a deleted function. So instead of discovering the mistake while debugging, the compiler catches it immediately. So it doesn't become a runtime error. If we comment it out, everything goes back to normal and everything is fine. Now, whenever you write a custom copy constructor for a derived class, you are responsible for the entire copy process. The compiler won't automatically redirect the base class portion to its copy constructor for you. The copy operation moves from the derived class down to the base class first. Once the base subobject has been copied correctly, the derived constructor finishes by copying its own members. Following this pattern keeps every layer of the object responsible for its own data. It's a simple rule, but forgetting it can produce objects that look correct on the surface while quietly containing incorrect base class states. So far, we have seen again and again that the classes that manage resources can't rely on the compiler's default copy behavior. We need to define exactly what should happen when objects are copied or destroyed. So, modern C++ takes this one step further with what's called the rule of 5. The rule is very simple. If your class owns a resource, like heap memory, a file, or maybe a network socket, you need to write one of the special member functions yourself, and you will almost certainly need the other ones if you need one of them. So, here's a table that shows all the 5 functions. The destructor cleans up resources, the copy constructor creates a deep copy, the copy assignment operator replaces the contents of an existing object. These two are new in C++11, the move constructor and move assignment. The move constructor transfers ownership into a new object, while the move assignment operator transfers ownership into an existing object. We will look at each of these individually. Let's start with the destructor. The destructor is probably the one you're already familiar with. You can see the syntax here from the slide. A destructor runs automatically when the object goes out of scope or when an object created with new is destroyed using delete. Its job is very focused. Release every resources that belong to the object. That's it. That could mean freeing heap memory, closing a file, or releasing a network connection, or whatever your class does. If we forget to do that, resources remain allocated after the object has disappeared. That's exactly what we call a memory leak. So let's write something like that, a tiny example. So here under lecture 8, let's go for example 5. Here we can create a buffer class, and let's say we have our data pointer. Here we will create a constructor. We will allocate some memory here. So let's say data new int 10. Now let's create a destructor. As soon as we write a destructor like this, we should immediately start thinking about the other 4 special member functions. So let's get back to the slide. Now we have copy constructor. Unlike the destructor, this one creates a brand new object. Its parameter is another object of the same class, usually passed as a const reference. The important point is that we are creating a deep copy. Instead of copying the pointer itself, we allocate our own heap memory and copy the actual data. That way, each object owns its own resources. So once again, let's go back to VS Code and let's see what we can do here. So now, go for buffer at first. we will allocate our own memory like this. And then now we copy the values one by one. So here, notice that I will copy the integers, not the pointers. So both objects can contain identical data, but each one owns a different block of memory. So here we allocated a new block of memory, and then we copied the data from there to here. As simple as that. This is the key idea behind deep copying. The objects have the same contents, but they no longer share the ownership or the same memory. Let's get back to the next one, which is our copy assignment operator. This one looks kind of similar, but it's solving a different problem. The copy constructor creates a new object, but the assignment operator works with an object that already exists. So imagine we have two buffers. Let's say we have W1 and W2, and then later we write it like this. We are not constructing W2, we are replacing its current contents. That means we first have to clean up the resource that W2 already owns before copying the new one. Let's write a simplified version. So let's get back to our buffer example. Here, first, we go through our syntax like this. Then, first, we protect against self-assignment. So, how do we do that? We say if this is equals to the other reference, then return this pointer. Then release the memory that we already own, and then allocate fresh new memory, and then copy each value from the source object like we did just now. Then finally, we return the current object. You can see that it is quite similar to the copy constructor. The big difference is that the object already existed, so we had to clean up its old resource before copying the new one. Now, so far, every time we have wanted another object, we copied the data. Let's get back to our slide. But copying isn't always necessary. Imagine a function creates a temporary object and returns it. That temporary object is about to disappear anyway. Copying all of its heap memory into another object would be just a waste of time. So instead, C++11 introduced new move semantics. A move constructor doesn't duplicate the resource. It simply transfers ownership from one object to another. The heap memory itself never moves, only ownership changes. The new object takes the pointer and the old object gives it up. No new memory is allocated and no data is copied. That's what makes move operations so efficient. So let's get back to our example once again. Let's go ahead with our syntax. Since we are constructing a brand new object, instead of allocating new memory, we will simply just say data equals other.data. And then we simply take the ownership of the existing pointer, and the original object must no longer own it. So we say that the other data is a null pointer, and here now this object will delete the memory. Here notice this one, the double AND, that tells us we are receiving an R value, which is typically a temporary object that won't be used again. Also notice the no except. We will come back to why that's important on the last slide, okay? Now, let's get back to the last one, which is the move assignment operator. This one follows exactly the same idea. The difference is that this time the destination object already exists. That means it may already own some memory. Before we steal the new resource, we have to release the old one. Otherwise, we would create a memory leak and that would be a mess. And that's what we are trying to avoid. So here the steps are simple. The destination object lets go of its current resources. Then it takes ownership of the source object's pointer. Finally, the source object is left empty by setting its pointer to a null pointer. Again, no memory is copied. The ownership is simply transferred. So let's go ahead and see an example. Here, let's write buffer and let's go ahead with our syntax like this. Now, just like this one, we will protect against an object to itself. So here, if this is other, then return this. And then release the resource that we already own, and then take ownership from the temporary object, and then leave the temporary object empty because we don't want that, and then finally return this object so assignments can be chained. Compared to copying, this one is much cheaper because where we copied, we had to do this, allocate new memory, and then put all the data. But here we are just moving the ownership. We don't have to duplicate an entire block of memory. So now let's finish with a few practical guidelines. First, think about the lifetime of the object. If the original object is meant to continue existing independently, then you need a copy. That's where the copy constructor and copy assignment operators are used. If the object is temporary or it's about to be destroyed, then moving is usually the better choice. Moving avoids unnecessary allocations and copies. Both move operations should normally be marked no except with the no except keyword. Why? Because the standard library trusts operations that cannot throw exceptions. Containers like standard vector can move objects much more aggressively during resizing if they know the move operation is guaranteed not to fail. That can make programs significantly faster. Then finally, there are classes that should never be copied at all. A good example is the standard unique pointer. It represents unique ownership. Only one object can own the resource. So in classes like that, we delete the copy constructor and copy assignment operator while keeping the move operations. So let's see what that looks like. Let's go for a new example 6. Here we will create a unique resource. So here in the unique resource, it will destroy everything normally. Okay. So at first we will declare the destructor and say that it should behave with its default behavior, but copying is forbidden. So we write our copy syntax and then we say delete so that it doesn't happen. Also, same for the other one, but moving is still allowed. So we will simply say that our unique resource no except is allowed, so default, and then our unique resource move operation, both of them are allowed. So this class, we could say that it communicates its ownership model very clearly. It cannot be copied, but it can only be moved. That's a common pattern in modern C++. You will encounter it frequently in the standard library. So that brings us to the end of the lecture. We started from simple member-by-member copying to the modern C++ rules and how things are handled. These things takes a little while to get accustomed to, and it takes some practice to get a hold of it. But in the end, it will help you to build safe code and safe program for whatever your purpose is going to be. So thank you. I hope we learned a lot of things together. See you on the next lecture. Bye bye.